Hello everyone and welcome. Let me say first, thank you very much for taking time out of your busy day to attend and participate in this webinar. My name is Jim Bostwick. I'm the Director of Marketing for C-REX Advanced Fabrics, and I will serve as your moderator today. As you know, the topic for discussion is the substrate uniformity matter. We have two speakers. Our first speaker will be Mr. Jim Walker. He's the President CEO of C-REX Advanced Fabrics. We also have Jay Forcucci, who is the Vice President of C-REX Advanced Fabrics. The presentation will take about 20 minutes. Following the presentation, we will send out a couple of quick polling questions, and we would certainly appreciate you participating in that. We will end our presentation today with a question-answer session. If you have questions during the presentation, please, we encourage that. You can actually post your question on the GoToWebinar drop-down menu any time during the presentation, and we'll respond to as many as we can at the end. You may also have noticed there is a file that is on the presentation on the drop-down menu. That file name is Substrate Uniformity Matters. It is a PDF file, and that file is there specifically for our participants today, so you can download that at any time during the presentation as well. So, with that said, I think I will turn it over to Mr. Jim Walker, President CEO. Jim, welcome.
Thank you, Jim, and thanks everyone for tuning in this afternoon with us. Our conversations about substrate uniformity, and polyester and nylon Spunbond substrates are typically used with glass or synthetic filter medias to protect the media during pleating and also while it's in use. Filters today are challenged with higher operating temperatures, higher pressures, and market demands for finer particle removal and longer service lives. We believe these conditions require even greater media protection, which makes the uniformity of the Spunbond substrate more important. During this presentation, we'll discuss ways to measure and compare Spunbond fabric uniformity, as well as we'll provide some case studies to illustrate how uniformity impacts filter performance. Spunbond uniformity is created through specific process technologies that are being employed in the manufacturing line. This includes methods to evenly distribute the filaments, multiple spin beams, and balancing throughput, which tends to drive lower costs, with the product quality objectives of the company. So nylon Spunbond has several advantages, and we'd like you to keep these in mind as we talk about uniformity today. The first one is its exceptional strength. It's 60% stronger than Spunbond polyester products. This gives it greater burst resistance at lighter fabric weights than what a Spunbond polyester substrate could offer. It's 24% higher temperature resistance than the copolyester materials that are often used in a Spunbond polyester as a bonding agent. This is the material that would start to weaken first in a high temperature application. It's 40% thinner than Spunbond polyester, which allows there to be more pleats and more surface area in the same size filter element. And finally, nylon has very good chemical compatibility with a variety of chemicals, and as you can see by this chart, it's more than 25% stronger than polyester after 2,000 hours of exposure to both diesel fuels as well as select hydraulic fluids. These advantages, combined with excellent uniformity, make nylon Spunbond a great filter media substrate. So when we look at uniformity, we look visually at uniformity, and traditionally have tried to judge the uniformity of different substrates with our eyes. As you can see by these pictures, there's thin spots and thick spots in both a 20 gram per square meter and a 34 gram per square meter sample. The problem with the visual comparison is it's subjective, and it's very difficult to do any kind of quantitative comparison. So my colleague Jay Forcucci is now going to discuss several different ways that we can quantitatively define uniformity. Jay?
Thank you, Jim, and good afternoon to everyone. In our effort to establish uniformity metrics, we really concentrated on two different methodologies. The first was physical properties. We specifically chose three different physical properties: basis weight, caliper, thickness, and air permeability. And then we also have here at our site a camera system. So we also looked at our online camera to look at transmitted light to try to understand the uniformity from that standpoint as well. Our sampling plan and test methodology for the physical properties, we actually purchased 6 different rolls of a North American high-quality manufacturer out on the open market, and we also selected 5 comparable rolls from our own production facility. And the basis weights, the range that we chose, really represent the types of products that are used in the filtration industry. About every 10 meters, we took a full width sample, and then we tested that sample in the CD every 12 inches. So every roll represents somewhere around 50 to 70 samples per roll. And on each one of those samples, obviously, multiple tests were chosen. And again, the ASTM test methods you see up there. Basis weight was chosen for a couple of reasons. Basis weight is obviously a test most people are very familiar with. It's an easy test to do and easy to get the data. But more importantly for us, basis weight also typically represents, there's a really good correlation with various strength properties. Mullen burst, grab tensils, strip tensils. So when we look at our data, we see a real good correlation between basis weight and those strength properties. So when we start looking at the variation of the basis weight during the testing, the green bars represent the nylon or the Cerex media. And again, you can see a range of 20 GSM up to about 50 GSM, or roughly 0.6 ounce up to about 1.5 ounces. Our product is a 4 DPF or 4 denier fiber diameter. 4 of the rolls that we bought on the open market are also a 4 denier. And you can see from just looking at the standard deviations that the Cerex material is much more uniform in basis weight variation than the 4 DPF. The 2 gold bars that we just put in there, those actually represent 2 DPF competitive product that was bought on the open market. And typically, the finer the denier, you would assume that the more uniformity that you would get out of that because you have more surface area with the fibers. In actuality, you can see our 4 DPF is still more uniform in basis weight than the competitive 2 DPF polyester product as well. Thickness variability or variation was the second physical property that we looked at. Our process here inherently creates a thinner product than our competitive polyester product, but also you'll see that our thickness variation remains fairly constant even though the basis weight and the comparable thickness goes up of that media. If you were to look at from a covariance standpoint, which is standard deviation over the average thickness, you'll actually see that the covariance goes down, whereas the competitive polyester product, you'll see the covariance stays, the percentage stays the same, and as a result, the standard deviation goes higher as the thickness and the basis weight goes higher. Again, you can look at it from a 2 DPF standpoint, the 2 gold bars, and again, you'll see that the variation with our product is substantially better. The important characteristics for thickness, especially in membrane casting applications where you're using the substrate to put the membrane casting on top of it, if it's a uniform product, and it actually creates a much more uniform membrane being formed on that substrate. And again, as Jim pointed out earlier, our product is thinner, which allows for a thinner composite profile. You can either put more pleats into the same area with the same open space for fluid to flow, and that increases your surface area. Or if you want to keep the number of pleats and surface area the same, now you've got more room for that fluid to flow around the pleats. Both of those typically lead to lower pressure drop, and in some cases can also enhance your dirt holding capacity. Air permeability is the last physical property that we chose, and we probably think this is the most important of the physical properties Typically, air permeability, at least the consistency of it, gives you a really good idea of how well the web is, the web formation is of the product. Again, when you look at the Cerex products, you'll see they're substantially better than the 4 DPF polyester product, and again, also better than the 2 DPF product. I'd like to make two specific comments on this chart specifically. If you look at the 34 GSM products, you'll see that the polyester Spunbond has a standard deviation for the air permeability at 159 CFM per square foot. So if you looked at that from a plus or minus 3 standard deviation approach, that range would represent about 950 CFM per square foot. And all of us in filtration know that whether you look in a path of least resistance, if you've got that kind of a range of product, you're going to have a lot of product flowing to one area and not necessarily to the other. So this is a really good way to kind of predict the thin spots and the thick spots, if you will, of that media. In comparison, if you look at the Cerex 34 gram standard deviation of 42, that gives you a range of about 250 CFM per square foot. So again, the difference in the ranges on a plus or minus 3 standard deviation approach, 950 versus 250. And again, that's a really good telling factor of the web formation of the Spunbond. The other point I would like to point out, and I'll get back to this in a second, but if you look at the standard deviation of our 34 gram sheet at 42 as compared to a 46 gram competitive product, again, it's about a third, 42 versus 122, and I'll get back to that in a second, but I wanted to point that out now. So our second method in looking at putting some metrics on the variation differences between our product and polyester Spunbonds, we have an online camera system that we installed 3 to 4 years ago, and it's used for online defect detection. In essence, we use grayscale output to determine the light transmittance, and that in essence shows us thick and thin spots, and there's a digital readout of the value. So again, we took the 20 gram samples of our product with a competitive product, and we also took 34 gram samples of or rolls, I should say, of our product and the competitive product, and we ran it through the camera system. And this bar chart here indicates the light transmittant factor in red for the polyester, and then again in green for the Cerex, and these are the 20 gram sheets, if you will. You can see from the number of data points, this represents well over 500 data points in each of those cases. So statistically, we think there's a lot of validity here. When we overlay the two, if you were actually to do a variance, comparison, variance being the standard deviation squared, the polyester would actually be 3 times more variable than the nylon product in this case. On the far right, you'll see in the circle there, those outliers there that you see in red, those actually would represent thin spots in the media, or areas where you don't have as much fiber, and that would be in some cases out of our specification for the same product. For the 34 gram samples, again, the red representing the polyester, the green the Cerex, similar type of a chart. You know, now the product is a little heavier, a little bit thicker, so you don't see as dramatic a difference between the standard deviations. But again, the Cerex being substantially more uniform than the polyester. And again, please note those thin spots on the side. So we feel as though the light transmitted data that we have here corroborates the physical data very specifically. And again, we think statistically both cases represent that the nylon is much more uniform than the polyester substrate. So let's get into some case study applications. The first case study we'd like to talk to you about today involves nanofiber process. And this is a process that we do not have ourselves, but we were involved with. Typically, the process was set up to run a 46 gram polyester Spunbond as the substrate that the nanoform is formed upon. Under the same machine settings, we actually came in and put a 34 gram or a 1 ounce Cerex on there. And again, if you remember, I pointed this out earlier, the air permeability of the 34 gram was 42, and for the 46 it was 122 CFM per square foot. So again, we were thinking the 1 ounce Cerex was a more uniform product. When you look at the data, you know, the one thing that does come out, it looks like the average for the Cerex is slightly higher penetration than the 46 gram. And again, this is done on a TSI 8130. This is probably because we were not able to optimize the settings and so forth, but really what I want to try to point out and what's more important for this thing is you look at the standard deviation. The standard deviations of the Cerex sheet show that it's about half the standard deviation of the 46 gram polyester sheet. So again, we think the substrate was more uniform, which allowed the nanofiber laydown process to result in a much more uniform sheet as well. Second case study we want to do is an area that we're starting to just now get a lot more involved with, and it kind of is concerned with hydraulics, trying to understand how the substrate affects the static flow, as well as now a lot of people are interested in the dynamic flow or the cyclic flow testing that's being looked at. Let me clarify up front, we do not feel as though our substrate adds any filtration properties. We think, again, it has to do with the uniformity of our substrate, which supports the filtration enabling media in this case. So what we did was we ran some flat sheet testings at an outside lab. We compared our 0.6 ounce and our 1 ounce in a composite for both static testing, which is done to the ISO 16889 test, as well as a new proposed standard for dynamic or cyclic testing, which is ISO 23369. In all of these cases, we took a composite which had epoxy-coated wire on both sides. It had the Cerex substrate on both sides, and then a 6-micron commercially available microglass media that's commonly used in the industry. We tested those flat sheet composites in a 200 square centimeter test area. The static testing was done at 6 liters per minute. The dynamic testing or cyclic testing was done between 2.5 and 10 liters per minute, and that was cycled approximately every 5 seconds. We ran the testing actually up to 125 psi. What we found was about halfway through the test, we think we started experiencing some bypass around the sheets because of the wires. So we're going to present to you just half the testing or 5 time intervals. But the other point I wanted to make here is a lot of people feel as though when you're using a heavier substrate, you're actually creating more pressure drops. So when you look at the clean pressure drops of these composites, you'll see there's 0.1 psi difference between the 20 and the 34 GSM sheets. The static, again, was done at the 6 liters per minute, and the dynamic pressure drop represents the higher flow rate, 10 liters per minute. So when you look at the chart, and we chose the 6-micron particle size and greater, you'll see that the 1 ounce in both cases actually shows that you're getting better filtration ratios or beta ratios through the first part of the test. And again, what you see is 5 intervals across the bottom. Once we got above the 5 intervals, everything looked like it started to kind of go towards the same type of a number, which kind of indicated to us there was probably some bypass taking place. Couple things to take away from this chart. Obviously, the cycle testing or the dynamic testing that was done is much more rigorous for the filtration media. But in both cases, again, you'll see that the 1 ounce provided much better filtration ratios than the 0.6 ounce. We saw the same type of effect at the 4 micron, the 8 micron, 10 micron, and if there's an interest, we can certainly provide you more data on this. You can contact us at a later time. So as a quick summary of the presentation today, Jim mentioned before, visually most people subjectively would say that nylon is more consistent. We feel in looking at the 3 physical properties that we've demonstrated statistically that the nylon is less variable than the polyester substrate. And then finally, using the online camera system, again, statistically, we feel like we're showing that the transmitted light data is also showing a much more uniform nylon media than the polyester competitive products. I'll turn this back over to Jim Walker for some conclusions.
Thank you, Jay. So based on this case study work, as well as feedback from a variety of our customers, we find that greater uniformity really does matter. As Jay showed in the case study with the nanofiber, but it also applies to feedback we've received from customers that do melt blowing as well as membrane casting, that the greater uniformity substrate provides greater filtration performance. It also can reduce downstream fiber migration, contaminant shedding, and channeling, especially in these very challenging real-world dynamic flow conditions. It provides better media protection during pleating, and it helps prevent burst failures from high-pressure system pulsations. Fewer thin spots mean the media is better protected, and there are less weak areas in the final composite that can allow a burst failure to occur. So when you combine the greater uniformity with the greater strength, temperature, and chemical resistance, what we call the nylon advantage, we believe it provides a superior substrate for today's demanding filter applications. Thank you very much. Jim?
Thank you, Jim and Jay. I appreciate very much the presentation, your comments. To all of our participants, as promised, I'm going to be uploading now a couple of poll questions. Should be very simple to answer. Would appreciate your feedback, if you will. So I'll leave the first one up for a few seconds, close that one out, and I'm going to be looking to see, we do have some questions from the audience, so we certainly appreciate that. I'm going to close out the first question, open up the second question. I'll leave that up for a few seconds. Close this one out. Looking at the questions, we will now go into I'll move along to a question answer session, so I'll close this out. First question, what polyester spun bonds were selected and why the roll sizes?
Yeah, thanks, Jim. That's a good question. Originally, we were trying to find full width rolls that would represent, both our full range of the profile, if you will, as well as the competitive product. And it was hard to find commercially available full width rolls. So we decided to look, in essence, at rolls that represented about half the line width, if you will. And then we made the assumption that the rolls were, in essence, from the edge to the middle, and that would give us the biggest amount of variation. Considering that typically in nonwovens you have a profile. We did the same with the Cerex products that were chosen, and that's kind of the methodology of what we did there.
Okay. Got a second question. Do you have more examples of how uniformity of the substrate is important in the filtration process or application?
Another good question. Without getting into specifics with some of our customers, I can give you some general examples. We have, for instance, one melt-blown customer that actually blows melt-blown on top of our substrate, and they are very particular with us in regards to the variation of our air permeability, so we have a very tight specification with them. And I believe, in conversations with them, they feel as though the formation of their melt blown on our product is dramatically affected by the variability of our air perm. So that's, one example, and we kind of touched base on that earlier in the presentation. Another area that we know of for sure, we have one customer that buys our product to cast membrane on it. And again, from a specification standpoint, very particular in working with us to try to minimize the variation in the thickness, and that's the area that we're working with them on, and that's one of the reasons why they've chosen our substrate. Again, that's something that's inherent in our process. We're starting to work a lot now with our customer base as our hydraulic and lube oil customers start to understand this new cyclic testing that's being discussed within the NFPA, National Fluid Power Association. And that's an area that we're just starting to get into, and some of our initial tests are showing that we think the uniformity of our product is actually affecting the final test results in this new cycle testing that's being established.
Great, Jay. Thank you very much. I think we have time for one more question. The last question for today is, can you provide more information on Cerex being used as a nanofiber substrate?
Thanks, Jim. Again, good question. This is an area that we're just starting to get more involved with as a company. I think there's two issues here. One, the uniformity of our product allows the nanofiber laydown to be much more uniform, and that's something we kind of presented earlier. Second area of concern, I think, or of interest, is a lot of the nanofibers that are being made these days through the electrospin process are actually nylon oriented. So we also think there's an affinity between the nylon electrospin fibers, nanofibers, if you will, with our nylon substrate. So we think both areas are affecting the uniformity of the laydown.
Great. Well, unfortunately, to all of our participants, that's all the time we will have today. I do see that we have several questions that we were unable to answer. What we will do is we will answer those questions immediately, and we will answer those via the email that you registered with. So no worries, we will definitely be in touch with you. If you need to get in touch with us, you can email us at our email address, which is on the screen, crex@crex.com. We'd encourage you also to look at our website, www.crex.com. Thank everyone so much, and have a wonderful rest of the day.